Thank you for inviting me. Thank you for coming. It's actually my first time in Ostrava. I've never been here. It's a beautiful city. And my apology at the beginning is that many talks here about the sophisticated, like really smart thing, while I'll be talking here about time series, which is something very simple. It's basically the bunch of the measurements at the regular time intervals. So you get the points, and you are drawing the lines through that point, like based on your style, you can choose what you want. And you usually draw the line and a bit to the right, that's called forecasting, and that's like all the fun. And the theory was developed in the 70s, mostly by econometricians. So those were classical statistical models. Well, if you ask today to the bunch of young people, like how they would do the forecasting, you know, they would say, of course, like that sounds a machine learning problem. And it's creating some tension because those two crowd of people are speaking slightly different languages, using slightly different tools. And sometimes there are not so actually many comparisons of the results from the first and from the other crowd. This is one of a few exceptions, the paper from the Plos One journal from the last year. It's actually one of the most read Plos One papers of this year. And why it's so much read? Because it's controversial. This is the leading author tweet summary, and he basically claimed that the best machine learning method was worse than the worst of the statistical one, and then half of the machine learning method sounds like a random walk. Is it true? Yes and no. But about this controversy, about this like tension between the statistical and machine learning words, will this talk be about? When you are speaking about something like dramatic, controversial, you should stay who you are and when you stand for, come from. So my current position is machine learning engineer at the CAI. So I'm currently in the machine learning world, but the most of my life I have been a biostatistician. So I'm coming from the statistical part. I actually had a PhD from statistics from the Faculty of Mathematics and Physics. And my path to the time series started quite recently. I'm no expert to time series. And it was during the snowstorm. Those days, I was the biostatistician in the small research lab in Maine. Maine is eastern coast of the US, close to reading Facebook of my Czech friends that were posting the spring photos on their timeline. And I was really unhappy. I was like, oh gosh, I wish to be in some like warmer place. And 2 months later I was interviewing to Google, and I've got accepted. And during the team matching phase, I was like speaking to a guy that was leading a small group doing the time series forecasting, and I admitted to him, you know, I knew nothing about time series. I was mostly working with mice, and mice do not live so long. And he said, like, you know, you could learn that, and that's what kind of happened. And a short legal disclaimer, I can't talk here about the internal technical Google stuff. If I say something that you think that I shouldn't have said, please tell me. But I can share anything that was made public, and I'm quite lucky here because something I don't know if you've ever heard about, unofficial Google data science blog, you can Google it. There is like a 2-year-old post about the tool, and that's more or less all what I need. Okay, but before I dive into that, let me say a bit what I mean by the time series data and some simple models for comparison and so on. So my data that I've spent most time on looked something like that. So it's a traffic data. Of course, I cannot show you the Google traffic data, so it's Wikipedia. Each point is 1 day, so on X you have the date, and on Y you have the number of the visit. It's log10 scale. The log scaling is almost always good model. What else can we like see say when we see something like that? It's going up and down. Why do you think that it's like frequently going here up and down? What is that? Any idea? Excuse me? I'm sorry, I don't hear you. Day night? No, no, no. Each point is 1 day, so it's not hourly data. It's week. It's day of the week. The people are much more like using the internet during the weekday than during the weekends. So it's a common pattern, but what's the main point? This is human driven. Like this data depends on the human behavior and will have like many things in common in any similar data. Another thing, if you look at that, it can be like well predicted. It's not like if you take some financial data, they are really hard to predict. This, if I'll tell you the day in the year, you can be like reasonably sure about the confidence interval. And you can see a forecast from the 5 different models. And you can see that some of them like get it quite nicely and some of them are really bad. So it sounds like the naive, but we will see that's what happens. Often, if I tell you this and you've never done time series in your life, what can you do? Like, there are some naive benchmarks. It's always good to try the naive benchmarks because you can then tell how much your sophisticated method is better, or even better observe that it is not, and it's actually doing worse than the naive benchmarks. Like the most simple thing is take the last value and carry it forever. Draw the line, or take a last few weeks of data and do the linear regression, and again, draw the line. Any other idea? What can you do? Like anything better? Like still naive, but less naive. Fourier analysis, yes, that's one possibility. Something even more simple. Like very good benchmark is just take your last month of data, last week of data, and like copy it, or last year of data and again copy it. And like really always try to compare to that because you would be surprised how like good those are. If you're in Python, stats models.tsa package is awesome. So you can use the exponential smoothing, you can use the moving averages or autoregressive models. You can try to decompose your data into the trend and seasonal and the reminder part. And something even like less naive but easy to use, some structural time series thing. This is a really good book. This is from the Rob Hindman. It's unfortunately written in R, so for Python you will need like to translate from R to Python. But it's still, I believe, like for many time series books, they are mathematically oriented. As I have said, the econometricians wrote them at the beginning. This is like really practically oriented. Like if you are not interested in math, but you need to do the forecasting, this is the awesome book. And it's available on the internet for free, so it's also a good thing. So let me now tell how the time series, something about time series forecasting tools at the Google and the Facebook. So this is just the copied picture from this blog post I've mentioned about. I'm sorry, it sounds complicated, but I'll go through it step by step. So the first phase is cleaning. So the red line is what you have, and the green line is the clean time series. And there are basically 2 things that you want to remove in this phase. You have the anomalies. That's basically for one day your logging system is not working and your traffic is way up or way down. And you have the level change. You do the new design of your web page, and from this date, all the traffic is twice as much. So because that would complicate the forecasting, you want to remove those things. So the first thing is basically somehow masked. And the second thing, you shift all the data up or down to not having the step in your data. The second important thing, and I think like most people use the time series forecasting tools because they don't want to deal with that. That's the holiday adjustment. So what's the difference between the holidays and anomalies? In both cases, you have the jump out, jump down, or jump up. The difference is the anomalies is something that is not connected to the forecast. You basically want to delete it and don't want to see it anymore. Why holidays is something that you want to remember because if you saw the Christmas effect in the last year and all the years before, you are likely to see it like in the future. Holidays are complicated. Like the good ones are happening every year at the same date, but then you have the Chinese New Year, you have the Eastern, you have the time shift between the summertime and like the day saving time and the classical time. So those are the things that you basically take care in this step. And you've got something that looks like this. And to make the forecasting easier, you want to decompose the time series. So the original is at the top into the seasonal part. And so this is the annual seasonal part. This is the day of the week, up, down. And this is the rest. And the good thing is that, like, for the seasonal parts, they are easy to forecast, even if they contain some trend. It's basically like you continue the cyclic pattern. And the rest, if you look at the original time series and what you've got at the very down, like this is much easier to be forecasted. At the Google, it's not done by one model, but you have the tens of model, and then you do some consensus like as easy as the median. You've got your forecast. You get everything back. You add the holiday adjustment, and you've got your forecast. If everything is working beautifully, it's awesome. If it's not, I want to just mention like one thing that could happen. You've got some anomaly in the middle, but it's like too long or something, so it's not detected as the anomaly. Due to that, your seasonality, like your day of the week effect, is overestimated. And if you look at the end for the forecast, you have the day of the week that is like way, way up what it should have been, and like people really don't like forecasts like that. Okay? Google never open sourced its time forecasting package. The good thing is that Facebook did 2 years ago. It's called Prof. It's both from Python and R. It's built on Stan, so probably originally it's coming from R, but the Python package is pretty decent. And if you look at the math, it's again decomposing the time series into the trend part, seasonal part, day of the week, and holidays. It contains the list of the holidays, so you don't have to like care about it. You just say the country or the global or what you want. And like it's targeted to the same time of the time series as what I have just been talking here about. So it's strong human scale seasonalities, day of the week. The numbers are high enough and so on. Okay. Competitions. Like I've mentioned the controversy at the beginning, but controversies have been here all the time. Like actually the same professor that tweeted this was really unhappy in 70s, where the cool hype thing in 70s was Box-Jenkins method that we today know more like the ARIMA, and they solved some theoretical problems and they were like really happy about their solutions. The only trouble was that when he tried it on the actual data, he got like better forecast for the he got the better forecast for the exponential smoothing, which is basically some ugly engineering hack. So he started a competition. At that time, the competition was not so much about the people, but about the method. He actually convinced some Box or Jenkins postdoc to do the calculations for him, originally on roughly 100 time series, then they expanded it to the 1,000. Then the M2 competition was not about the time series, but M3 was again, and that time it was a 3,000 time series. They were taken from like very different areas. So it was the business, demography, finance, economics, and that kind of force you to do the forecasting of one time series at a time. You can't like use the method. The winning solution was the theta method, something that didn't seem simple, but later it was like shown that it can be reformulated in the more simple way. And from the beginning, from the time they like put the results of the competition, people debated it quite loudly because they didn't like it. Of course, those they didn't like win, didn't like it, but there were the real issues, like the possibility of the cheating, because the time series were taken on the real data. So if you were motivated, you can like find it like which time series it is, and then you know the future. They were like the commercial softwares that actually the second place in this competition was the commercial software that never like open source its solution. So like, was it real or not? It was hard to say. And the last thing, and I believe will always be in those type of the competitions where the interpretation, like on those data, those methods are better. Can we like, does it say anything in the general case, like for the general time series? Okay, and last year they do the M4 competition when they try to address at least some of those issues. So it was 100,000 time series. They do not only the point and estimates, because some people are more interested in some like 95% prediction intervals, and all the solutions must have been reproducible, put on the GitHub or something. And what is like important, what is the takeaway from this competition, is that all, I believe, top 15 solutions were some kind of the combination of like simple solutions. Like the winning solution is combination of the neural network, recurrent neural network, and the exponential smoothing. Now, if you are the deep learning engineer, you must be now, wait, what? I don't really believe you, because the deep learning like changed many areas in the last 5 years or 7. Like for the image recognition, you know, now it's basically deep learning field. Audio recognition, natural language processing, in all of those neural networks did wonderfully. So you are telling me that they can't draw the line through a bunch of points? That doesn't make much sense. And the answer to this is, first of all, they totally can draw the line, some lines through the bunch of points. If you Google using LSTM for time series prediction, you've got hundreds of thousands of hits. My problem with many of those things is they don't really compare to the other solutions. And some of the data they were using are like hard to tell whether they are going right or wrong. Like if I have seen on S and P500 share index, it's like, you know, is it successful or not if you draw the line through this? And really, what's the trouble here is the dimensionality problem. If you have only one time series, you know, as I have shown here, 2.5 years of data, you have less than 1,000 values. This is part of the Keras code that is probably hard to read that I'm using for the time series. If you count the parameters that are in this model, it's hundreds of thousands parameters. So you are fitting 1,000 values, you are fitting 100,000 values, and your actual data are 1,000 numbers, less than 1,000 numbers. So you have the dimensionality problem. And of course, deep learning like did awesome stuff like not to overfit, but it's like really, really hard. So does it mean that neural networks are not good for the for time series problem? Absolutely not. And to show here like one example when neural networks beat it, statistical methods, is Wikipedia traffic data set. It was originally the competition on the Kaggle. And if you look at it, I was actually using the data in the figure before. So it's the goal was to forecast traffic to Wikipedia pages. It was from 6 languages, different mode of access, so it's roughly 150,000 time series. The training period is slightly over 2 years. Why we do need 2 years? Because if you have just 1 year, it's impossible to distinguish whether, whether this peak is one-time event or whether you will see it like every year. So you need at least 2 years of the data, and the metric was SMAP. I must skip it. I might skip it. And this is the results. And from the top 8 results, 7 were neural networks. There is one exception. If anybody of you know Kalman filtering, they were like really smart way how to use Kalman filter, and the guy score, I believe, number 6 is Kalman filtering. So why is this possible? This is possible because, by the way, many people are trying Prophet, this Facebook time series solution on this, and there was like, nobody was successful with that. How is this possible? Like, it's like, I'm contradicting two things. First of all, those time series were relatively short, just 2 years of the data, 2 years and 2 months, I believe. So it's like the minimum what you can do for the statistical forecasting, but ideally you would like to see 5 years of the data or something like that. And second of all, because you have the data that are like same in nature, you can like bring the information between the time series. So you can like learn on one time series and use it at the other. And it appeared that this is what the neural network are really powerful at. Also, if you look at the sum time series for the statistical model, it's kind of challenging, like to detect those changes and like correctly like change the model. It's not impossible. The change point problem, it's basically the whole subfield in the time series, but it's not so hard, like easy to do. And last but not least, if you look at the traffic and the traffic patterns, like the majority of those time series were like not so much accessed. So if you have the data that looks like 0, 0, 1, 0, 0, 2, 0, 0, 1, like, and you're fitting some Gaussian models through the things like this, you will not be much successful. Okay, so the classical or machine learning methods, like why don't we have both? My general like rule of thumb is if you have a few time series, like 5, and you have like 5 years of the data, I would bet on the statistical methods. And I have seen like many times when people were doing the deep learning and then somebody come with some exponential smoothing, which is like, as I've said, like engineering hack on the 2 lines of code, and beat this neural network method. If on controversy you have like the short time series and they are somehow clustered, so they have something in common, then deep learning is likely to be either as good or even better than the statistical parts. So that's all from me today, and if you have any questions. Actually, if you have any questions, I was given the sweets.
Thank you very much. So I wanted to remind everybody we have Slido set up. You can enter the code PyConCZ. We are waiting for your questions. Also, if anybody would like to ask a question quickly, I can run around with a microphone. Please don't make me run. Use Slido. I encourage that.
Okay.
There are sweets for the best questions.
For any question.
Wave at me if you're trying to ask a question. I don't see anything on Slido. All right, that will be it. If you'd like, you can catch Petr later. Thank you very much for your talk.
Thank you for having me.